why would this shape fall, and why would this kind where every node has
it's working. Okay. All right. So as usual, I start by reminding you a little bit about what you were doing last time. So I think I can start here. Okay, so we have seen in the previous lecture that some complexes of presheaves that enters in the composition of some particular quotient. Of course, here quotient is in quotation, so just something that goes from omega, so quotient of omega, the T spectrum omega. So some of these complexes, where strongly rigid. And we've seen also that as a consequence of strong rigidity, we can compute the psi HH star, or their psi HH cohomology can be computed in some sense more algebraically. Again, let's put this into quotation. You can express the cohomology without having to use very complicated foliation. In the sense, so what I want to do today is somehow to use this fact here to express in a better way this quotient of omega, and make this somehow more precise. What I mean by can be computed more algebraically. And to do this, I need some. So this is paragraph 5.6. I would need some preliminaries on stratifications. And so after this, then I can explain what I mean by this more precisely. Okay, so let me just to fix notation, remind you what is a stratification. So I only consider stratification on Noetherian topological spaces. So let X be Noetherian topological space. So a stratification that I usually denote by S like this. So this is mat SCRS in LaTeX of X is a set of locally closed subsets of X called strata, so called. And if I have more than one stratification, I would say S strata. Otherwise, I would usually say just call this these elements strata. So they are locally closed and also connected. So connected, locally closed subset of X, and such that the usual two conditions. So first, of course, we want this to form a partition. So X is a union, disjoint union as this. So set theoretically, of course, of strata. And second, the closure of a stratum is a union of strata. This is the usual notion of certification. So here are some remarks about this. Okay, so as before, so if I have there is so first the set of strata of S strata is finite and has a natural order. Okay, and so we say that the stratum is smaller than, so we write S smaller than T to say that S is inside the closure of T. The maximal strata for this relation are the open strata. So meaning that the stratum which is an open subset of X. And of course there is a so-called the coarsest stratification. This is the one which has strata or connected component of X. And more generally, there is, of course, so-called, we can say a certification is finer than another. So, okay, I don't know. We can speak about S finer than T, has the obvious meaning. Okay, so yes, I should say also, maybe I should have said this, I think, the definition, but let me say it also here. So just maybe a point of terminology. So we say that so given X and certification, we say that a subset T inside X is constructible, is S constructible. And this means that it is a union of strata. So I can make this a bit more precise here. So we say that S is finer than T if every stratum in T is constructible for S. Just an example, maybe, or a construction. So this is so given a family, a finite family of closed subsets in X, there is a coarsest. There's a coarse stratification for which the I's are constructibles. And we can write it down. So the strata are exactly the connected component of the following subsets. So you take an intersection. So you fix a subset G inside I. So this depends on G inside I. You take the intersection of the closed subset in G, and then you remove the union of the other. This is G. Okay. Let me also put maybe a definition here. So of course, if we have a continuous map between Noetherian topological spaces, we can, and if we have stratification, so S on X and T on Y, we say that F is compatible with the stratification if the image, so for all C, for all D in a T stratum that exists, of course it will be unique C and S stratum with the property that FD is contained in S and C. And you can reformulate this in an equivalent way. So this is equivalent. Maybe a nicer way to say this is that F minus 1C is T constructible for all C stratum, for S stratum C. Okay, so these are. Yeah, these are somehow the only reasonable definition you can imagine. So I just wanted to say this to avoid confusion later. Oh, yeah. Yeah, thank you. Okay, so whenever we have a stratification, we can speak also about flags. This is also the kind of the obvious notion. So we take again X topological space, Noetherian, and with stratification S. So the flag, and sometimes I would write S flag if I need to make this precise, is a sequence of strata, that I usually denote by D underline, and it consists of, so it's an n tuple like this. These are stratas, and of course such that you ask that it's ordered. So I want D0 smaller than Dn, and I want them to be smaller and different. Okay, so it's a strictly there's no strictly increasing sequence of strata. This is a flag. Okay, so here's a notation. So I denote by FL X, comma S. So this is a set of flags. And but I think about this as a category. So considered as a category where I declare that there is a map between a flag D to a flag C if D is a refinement of C. Right, which means that the strata that appears in C, they also appear in D. So it's like inclusion, but written in reverse order. Okay, so here's a fact. So take f y to x, C0, and compatible with stratifications D and S. So we have, there exists an induced, or there exists a functor f lower star that goes from flags on Y to flags on X. And what does it do? So it does the obvious thing. So if you have, okay, let me write it like this. Okay, so it sends D to C with the following property. So C consists of those strata that contains the image of a stratum in D by F. Okay, so this, right. So in fact, there is a similar map on strata. In fact, so whenever you take a stratum in Y, there is a unique one in X which contains the image, and this is F lower star of the stratum, and then this extends to flags. So I will, we will use the following. We need the following construction. Okay, so let X now be an Euclidean scheme. Endowed, endowed with a stratification S, such that, so I assume the following condition, every stratum is closed in an affine open subset in X. And so such stratification will be called affine from now on. So such S is called affine. Okay, so assume that we have such a thing, and let d0 to dn be flag for the stratification. So we define somehow the completion of x along the flag. And this is sometimes also just written x d0 up to dn by induction on dn. By induction on n, as you can imagine. So if n is 0, so we do it like so. So we first say what is x d0. So this is simply the completion of x, or maybe let's say of x on along d0. So again, this is as usual. So what I mean really here is that this is the spectrum of. So what you do, you take an affine neighborhood of d0 in which d0 is a closed subset there, and then this is the spectrum of the completion of the ring of function on this affine neighborhood along the ideal d0. Okay, and then you define x d0 up to dm. This is just the completion. Of x minus 1, of course, along the inverse image. All right, and it's not difficult to see that this is, and this somehow explained the convention there, so that there is the map sending d to x hat d defines a covariant functor from flags to schemes. Let me say it orally. So if moreover x happened to be, for example, an excellent foliation, then these are also excellent foliations. And the natural map from the completion to x, from this guy to x, is of course diff et al. Okay. Okay, so I continue with another construction. Okay, so now let's take f to be a pre-sheaf on excellent foliation. Let's say over some base. Yes. Let's fix x be an excellent foliation, and let's give also ourselves as an affine stratification of x. Okay, so then we define the following object. So so chi index x m. So this is something which takes the certification and f and give you the following thing. So this is a product over all maps between flags, all sequences of m arrows between flags. So this lives in the category of functors from the simplex m to flags. Okay, so and then just take the value of f at the completion at the flag d0. So why do we do this? Because this defines naturally. So this defines an augmented, so a co-augmented co-simplicial object that we just denote by chi x maybe with a dot sf. Okay, so in fact, this is if you have seen this is simply the co-simplicial model of the homotopy limit of the diagram, which is indexed by flags and taking a flag to this to f. Okay, so maybe let me write it. So this is a co-simplicial. So this is somehow so-called Bousfield model of the following thing: homotopy limit over flags x of f. Okay, so here's a simple fact is that if we have a morphism in x s and stratification Ts, of course, compatible with f and both are affine, then there is an induced morphism f upper star between these co-simplicial objects. Okay, so I will not write it down. It's not so difficult. So, but basically, you use this functor f lower star from flags on y to flags on x, and just inverse restriction for the pre-sheaf f.
Is supposed to be compatible with these?
Yeah. So f is plus compatible with f. Yes. Okay, so this we can use this to make the following construction. Okay, so construction. So let's keep the same assumption as before, and let's now. So we define x dot x f. So this to be the colimit over all stratification of x, which are affine stratification of x of these complexes. Okay, so this makes sense. And because of the previous fact there, this defines a co-simplicial augmented, co-augmented, co-simplicial pre-sheaf on excellent foliation. Of course, in degree -1, this is simply f. Right? I should have said this before. So. So this conceptual pre-sheaf is denoted by just chi of f, and so so I call this so this is called the formal Godman resolution of f. Right, so it's it's somehow kind of similar to the Godman resolution. And somehow this also terminology is kind of motivated by the following proposition. So now let's take f to be a complex of pre-sheaves on x for s. Then the natural map from f to the total complex is Zepsini-Snevich local equivalence. So maybe let me say it also orally. So when I write tot of chi, I mean that I somehow disregard the augmentation. I just think about chi as a co-simplicial object, and I take the total complex. When I write tot plus, then I mean that I take into account the augmentation. It will be the cone of the augmentation. Okay, so let me maybe just quickly say some words about the proof of this. Okay, so let me sketch the proof of this. So let's just assume that F is a single sheaf, single presheaf. And let's so we want to show that this complex is locally acyclic. For the Sini-Slevich topology. So we take, let's let alpha be, so cohomology class over some x. And so we want to show that alpha is locally 0. So this is what we want to do. Now alpha somehow by construction, alpha comes, it's the image of so alpha 0, which is a cohomology class of the complex chi, maybe dot plus chi x for some stratification f. Now the point is that whenever you have such a stratification S, then you can look at these maps. So this forms a cover for Sini-Slevich topology, Sini-Slevich topology. Yeah. And so this means that we can replace X by one of these guys, and somehow we may assume that X is complete along the closed stratum. Okay, and now now the point is that whenever you have a flag in S, then the completion along this flag of X is also the same as the completion along the flag where you adjoin C. In case C is not in D, we have this. Okay, because X is already complete and at C. And so somehow this means that now the idea is that this diagram comes by inverse image or by restriction from a diagram on the category of flags over C. This is the category of flags with a map to C. It means that these are the flags that contain C. Okay, And now the point is that this has a final object, and therefore a homotopy limit over this is just the evaluation at the final object, and this somehow gives you what you want. Okay, I think there are probably many different ways to see this also. But. So, unfortunately, I will need to extend these things to the context of star foliation and star schemes. We need extensions to the star context. So I do this very quickly, just again to fix notations. So here we now consider X star, a star topological space, which means that it's just given, it's a continuous map topological space, and assumed to be Noetherian. So what is the stratification here? So a stratification, S star is simply just consists of two stratification, S0 and S1 on X0 and X1, and of course we ask that the map from X0 to X1 to X0 be compatible with these. This is stratification. Then and what are the flags in this context? So so I mean, maybe I just flags are usually just flags on X1. Okay, and this is clear why we don't need to specify a flag on X0, because a flag on X1 determines a flag on X0. And there is the same construction as before. So if we have X star Noetherian scheme plus stratification, and if you take a flag of X1, then we define X hat star D stars. D underlines this is really X1 hat D, and then X what 0 C, where C is the image okay, and then you can also do you can use this to also to define a formal Godmon resolutions for pre-sheaf on let's say X foliation over some base P star, exactly in the same manner, except you just take flags over X1 instead of taking flags over. I mean, you have to take a colimit over flags on both X0 and X1, right? Or you have to take a colimit of star stratification if you want. But I don't. Should I write it down, or it's really clear? It's okay. Okay. And you have the same proposition that we get some kind of a resolution when we do this. Okay, so now let me explain the application of this to somehow the thing that you are interested in. Okay, applications. Okay, so yeah, so remember we have this complex of presheaves on this this criteria of foliation over a diagram, which I will not recall, but okay. And somehow we have seen last time that if we take O star tensor with some power and tensor with this guy, then what we get is strongly rigid. This is what I explained last time. Okay, so we want to use this this fact and some of what I just explained now to prove the following theorem. Okay, so the obvious that goes from O star tensor M to the following thing. So you take total complex of the Godemont, formal Godemont resolution applied to this guy. And then you make this fibrant for the HH star topology. So you have this obvious map, and the claim is that this identifies the left-hand side or the right-hand side with a psi HH star fibrant replacement of the left-hand side. Okay, so what does it mean? It means that this is, so this means two things. This is a psi HH star equivalence, local equivalence, and the target is psi HH star fibrant. So the main point, I mean, okay, let me say it already. So this fact here is clear now because we know that without taking fibrant model, we know that this map here is a local equivalence for a topology which is even weaker than this. Is a psi Nisevich topology with a star maybe. What is really new in this theorem is that this guy here is a CHH star fibrant. So and why this is not an obvious fact, because here I only took a fibrant model for a much weaker topology, the HH star, and I'm claiming that the result is fibrant for a stronger topology. So this is like saying for some presheaf computing the Nisnevich cohomology give you the Etel cohomology, for example. Okay, this is a similar statement. And so this is somehow really the content of this is that it gives you somehow a nice or a more manageable model of the CHH fibrant replacement of this presheaf. Okay, so I try to explain the proof of this theorem. So as I just said, so the statement is equivalent to say that the natural map from this complex made HH star fibrant going to the same complex but made Psi HH star fibrant. This is a quasi-isomorphism. This is what we need to check. Now, since both sides, so since both sides are, in particular, are HH star fibrant, it is enough to show that this is an HH star local equivalence, which means that we can argue locally for this topology, and but we know what are the points of this topology. These are given by star polytray with some condition on the fraction field. So we see that it's enough to prove the following statement. I'll just restate. So proposition. So we fix a K star polytray V star such that, also I think this is not even important for the proof, this condition, but so such that the residue field, the fraction field are algebraically closed. And these are exactly the points for this topology. And so this condition will come up later, so I give a name to this. So we say that that V star is saturated. I remember last week I was speaking about formally saturated polytray. So here it's only saturated, and this is of course a much weaker condition than being formally saturated. Okay, so we fix such a thing. Then the claim is that gamma of V star, so sections, global section of this thing, so not write it. Going to R gamma CHH star. So this is the cohomology for this topology of, again, of the same thing with value in this complex that we are interested in, the thing which is here. This is a quasi-isomorphism. And then somehow it becomes clear now why it's interesting. So why the work that we did last time will be helpful here, because what I explained last time was exactly somehow the aim of it was to be able to compute the cohomology for this topology of object of this form. Okay, so we will use this somehow to prove this fact here. Okay. So I'll try to sketch the argument or the proof of this proposition. So maybe without entering too much into the details, but at least telling you what are the ingredients. So maybe here are first some remarks. This is an obvious one. This complex here is strongly rigid, and this is because, so since it is CH8 star locally equivalent to that thing. And we have seen last time that this was rigid. This is the first remark. Another remark is the following. So how should I understand, how can I understand this complex here, for instance? So remark that V star has a coarsest, has this finest stratification, which is given by the course, so such that strata are equal to the points. And it turns out that in fact, so one has to be a bit careful, but one can prove that for every f complex of presheaves, the value of gamma V star at the Godman complex, Godman resolution. So let me maybe put an M here. So this is given as follows. So this can be written as a product over all flags. Now I write the flags like this, like point underlined. Map of flags. So this will be and then evaluated at f of V completed star at the point, at the flag. One has to be a bit careful when defining this, but Maybe I don't. I mean, you have to take the natural definition. Okay, so you have to write V as a co-limit, as a limit of stratified excellent foliations, and then do this on the level. So at each level. Okay, did I write it down? Okay, so let me say so. So how do I? So maybe just a parenthesis. So let's take V polytre in this category. Yeah, any. But let's just take. So this. So V is you can write it as a limit of some system, say, of projective limit, co-filtered of some VAs, where the VAs belong here. Okay, so I mean this is what I mean. But when I said a polytre here, it means that it's given as a limit like this by definition. So now let's consider the set of tuples like this. So where you take A and A, and this is let's say affine stratification of VA. Okay, so this is of course this is still a co-filtered set, and then then somehow this guy here is defined as a pro object, pro foliation indexed by A prime, and so to such so it's given as a limit of a S of what? Of VA completed at the image of the flag psi. Right? So of course the map from V with its final stratification to VA with S is a stratified, is compatible with stratification. So you can speak about the image of the flag, and you can complete this there. Okay, this is what I mean by this object. So it's really a consequence of the definitions, but one has to think for a few minutes to see this. Okay, so this has a very nice consequence. This I think there is a problem with this. They want to update. It's working? Okay, then fine. Because, I mean, here it's not working. It's working, but there is a message saying that there are important updates which are pending. But I think that's okay. Fine. No, but I think we should maybe not touch it, otherwise. Okay, yeah, later. Okay, thank you. All right, so as I said, this has the following nice consequence. This remark. So as a lemma. I mean, okay. So let us set F to be this guy. I think until the end of the proof, f will be this object, this pre-sheaf. Okay, so let v star as before, so as in the proposition, and assume that with length of v1 smaller than 1. So okay, then the square like this is so gamma of eta v tilde star, and this is again the tilde from last time, right? Which only makes sense when v has length 1 of the Godman complex resolution. Okay, so same thing. It's eta. So this is homotopy Cartesian. Okay, so why this is the case? So let's see. So yeah. So v1 has 2 points, right? And therefore 3 flags, namely the flag sigma, the flag eta, and the flag sigma eta. And so since we are really, since the Godman complex is really computing the homotopy limit, so we see that in fact we have this Cartesian square. For the Godman resolution of anything, not necessarily. So this will be the completion at eta, the completion at sigma eta, and this is the completion at sigma. So now the point is that this square identifies with this square here. So it's clear for this part. This is just the generic point. But for this, you see this is so remember v tilde star sigma is a closed thing here, and we have seen so since my thing here is rigid, this will be an isomorphism because you can. So this will induce an isomorphism when you evaluate your complex of pre-sheaves, because you can replace this by the closed point, and they have the same closed point. Okay, and the same for this and this. You have to work a little bit more, but we have seen this last time while proving that this was rigid. Okay, so this gives this, and as a consequence, you see that the proposition is okay. So this has a consequence that proposition is okay if the length of v1 is smaller than 1. Why? Because we have the same Cartesian homotopy Cartesian square where we put if we put our CHH star everywhere. Okay, and so by comparing the two squares, we are left to check that this and this induces are the same, and this is clear because everything is a field or is formally complete formally local. Okay? And so now we want to try to get to higher, to longer somehow valuations by induction. And okay, so I try to be quite rather quick on this. It's really somehow the same argument that we have seen last time, very similar at least. So let me make this definition, which will come up also later. So this is the notion of a regular stratification. So we assume that X is a regular scheme or regular excellent foliation. So we say that stratification S on X is regular if it is defined, or if it's associated, to the reducible component of a strict normal crossing divisor. So what I mean is you have a normal crossing divisor on X, and you look at the stratification, which is the coarsest one, for which the reducible component are constructible. Okay, so this is just you take intersection of reducible component and you look at the connecting component, and these are the strata. Okay, so here's okay. So now we start to do some of the induction, if you want, on the lens, and for this we need a few lemmas. So here's the first one. Okay, so F is the same as usual. So take X star be a regular excellent foliation with a stratification which is also assumed to be affine and regular. Now we take two flags on X1. Sorry, this is on X1, and this is on X0. So this is image of D in X0. Okay, so now let Y star, we define Y star to be the closure, so it will be, yeah, simply the closure of dn mapping to the closure of Cm. So this is a closed sub star foliation of X star. Okay, and so the claim is that the obvious map from F to completion at the flag D to the completion to F at the completion of Y at the same flag is a quasi-isomorphism. This is actually quite obvious that this is true. So I just write a line why this is the case. So, so the point is that you see the X, so the completion. So either 0 at 2 or 1 doesn't matter of D. At D, this is the same as isomorphic to the completion of Y, 0, 1, at D, plus some extra formal variables. This is, of course, might depend on 0 or 1, but if we fix 0 or 1, we have such there is such an isomorphism. Okay, why? Because Y is a smooth subscheme of X. Yeah. It's somehow, I mean, somehow in the definition of this guy, so that is the last completion, which is the completion at D0. And at D0, or rather the inverse image of Dn, sorry. And the inverse image of Dn is exactly this guy. Okay, so we are completing, so we have this. And since F is essentially given by the ramp cohomology of so and since this map induces the ramp isomorphism on the ramp cohomology, somehow the result follow. Okay, so I mean there are the ramp cohomology and there is this O star over line, but also on O star over line, the way it was defined, it gives you isomorphism when you evaluate on these two guys. Okay. So this is okay. Another lemma of similar nature is the following. So now we take yeah. Now let's take X star again. B so maybe X or star. Assume it to be regular star foliation. We fix also regular stratification on X star. Now we take two flags. D and D prime. And we take also a morphism between them. And you assume that we have the same end strata. So I assume that d0 is d0 prime and dn is d prime n prime. Okay, so then the induced map from F, sorry, and the induced morphism from F completion at d prime, so this is a natural map, is an isomorphism, is a quasi isomorphism. And somehow the value on the flag does not depends only on the endpoints. Again, I only sketch the proof. Just tell you what is it about really at the end. So the point is that you can write down. So you can write. So of course you reduce to the case where d prime is given by d0 and dn. This is only need to consider this case. And so I tell you how the completion look like in each case. So the completion of x1 at d, it can be written as follows. So it's isomorphic and of course non-canonically. So what you do, you take d0, you add formal variables for some system t1 s1. So these are system of variables. It's not only one variable, but system of them. And then you inverse. You add the inverses of the variable in the second system. Okay, so it's like completing and then removing a few divisors. Okay, and then you repeat this. In fact, as many as flags you have. So I think Tn, Sn, and then you invert Sn. So this is the completion with respect to the first flag, and the second one is similar but simpler. So here you have again d0. You have formal variable, but what you do, you take all the variables before the variables before. Okay. And then you invert the S's. Okay, that's it. Okay, and so similarly for x0. Okay, we have these isomorphisms. They are not canonical, but somehow the map from this guy to this guy is the canonical one, is the one that you think. Okay, but somehow the map from x1 to x0 is not the one that you think. I mean, it cannot be written in coordinates a priori. Okay, but somehow this is somehow enough to conclude, and I try to. Okay, so but because of these facts, it's now it follows that the RAM complex of x 0 or 1 completed at D of the prime mapping to the RAM complex completed at D. This is a quasi-isomorphism. And similarly, the category of model with rectangular connection of logarithmic type on that thing is quasi-isomorphic to, so equivalent to make log. Okay, and from this somehow, and going back to the construction of why you can conclude. Okay, I mean, for instance, this thing here is really kind of easy. You have formulas for the RAM cohomology of such a thing. When you add from a variable, you don't change the RAM cohomology. When you invert things, you add some kind of residues. Okay, so it's really very concrete. Okay, so and so using these two facts, so we see that. So with some, I will not be able to repeat this here, but with some formal manipulation with homotopy limit and so on, you can then prove quite easily the following lemma. So again, f as before, now v star as in the proposition that you are trying to prove. We take here d1 inside v1 open, z1 inside v1 closed. We assume that they intersect. And then we have we have a Cartesian, a homotopy Cartesian square like this. So and here we have the Godemont complex of f and so on. Okay, and so as I said, this is really you're just using the fact that we are in a rather simple situation. The value of this guy on for example here on V star is so it's the homotopy limit of some diagram of complexes indexed by flags. But we have this, since we have these two lemmas. In fact, this diagram is really simple. It comes from a simpler diagram because somehow, as I explained, for instance, the value of this pre-sheaf depends only on the end point of the flags, for instance. So it's a rather simple situation, and then you can somehow play a little bit with this and prove that such a thing is homotopy Cartesian just by formal reasoning on homotopy limits and the shape of the categories that you are dealing with. So you get this. Once you have this, you are done because we have a similar square where we have r psi h star, okay, from last week, and then now we can use induction on the lens to see that this is the same if or not we put this r psi h star, and then we get the same for this here, and we conclude. Okay, that's the end of the proof. Okay, so let me finish this chapter with just restating what we need to remember for next time. Okay, so here's what we need to remember. So there exists a morphism, let's say of algebras, maybe, of T spectra over this category of excellent foliation between the Durham complex, the spectrum representing Durham cohomology, to this guy, singular complex lambda infinity dot direct image by lower star p lower star of now we can put the, thanks to the previous theorem, we can put the total complex of the Godemo resolution of the spectrum sigma bar t infinity of the complex y, and all this has to be made fibrant for the HH star topology. And of course, the crucial thing here that we can just put HH star instead of putting CHH star. This is really the main advantage. Okay, so why this is somehow better better than the same statement that we have seen before, where we had here something maybe slightly simpler, just this guy maybe made CHH fibrant. So the main advantage of this formulation, so the main advantage here is so that's it, is that we use the HH star topology, and this has the following consequence, that if I'm interested in, so if I only care about values on smooth varieties, smooth schemes, then I can do the following. Then the right-hand side can be obtained somehow more algebraically as follows. So first, you restrict this spectrum here, sigma t. You restrict the Godemo maybe the Godemo resolution of sigma t infinity y to the category of scheme of finite type over p star, of course, with this indexing category. Okay, so this is of course this is a subcategory of the category of foliation over p star. So I can restrict this thing, and we will see later that this thing has a very nice description over this category. We can restrict this and then replace it by an HH star fibrant model, which makes sense because the topology HH star is well, it can be restricted well to the category of finite type schemes. There is no completion anymore, so there is no reason to. We can restrict it here, and then take direct images and so on, and then apply these operations here. Okay, so this is somehow the advantage of this statement here. And so the next chapter will continue in the same spirit. So what we will try really now to understand the restriction of this complex to this category and try to even somehow get rid of, because here we still have some completion, of course, involved. This is the formal Goldman resolution, so there is some completion around, and so we see that we can even get rid of this completion when we work over this category. So this will be the subject of the next chapter. I don't know. Is this clear what I'm trying to do, or yeah? If you have any question, please ask me. So this is chapter 6. So here we will get, as I promised, the purely algebra, maybe geometric model of, I don't know, let's call it Y. All right, so for this I need more about stratification and more precisely about regular stratification. So I start with some complements or just paragraph about regular stratification. And this will be actually part 1, and we will be constructing some torsors here. All right, so it will be practical to make the following definition. I could have made maybe before, but I'll do it now. So a stratified scheme or foliation is just, of course, is a Noetherian scheme or excellent foliation with a stratification. Let's call it X with a stratification that I usually denote by S index X. So we say, so we speak about, we say that X is regularly stratified if the stratification is regular. And also, when I write FLX, this I will mean, of course, with respect to this stratification. Okay, so now these objects, they form categories, so I introduce some notation for them. So I'll denote by scheme sigma as this is the category of stratified schemes. So inside we have the regular one that I denote by reg sigma S. So these are the regular one, subcategory of regularly stratified schemes. We also have the finite type version, so I will write them like this, or S, or and so on. So obvious meaning, and also the foliation part, x full sigma, and so on. Of course, the maps here are maps which are compatible with the certifications, obviously. Right, so in this section, I will somehow gather some construction that only makes sense when the certification is regular, as far as I know. Maybe it makes sense in more general, but I didn't try to do this. Yes.
Do you also use some notation or something to denote when those are affine? Would you need that?
Yeah, right. Yes, I'll do. So, and then I will write it like this, I think. For instance, here. I put, I think I put just an AF here. This would mean the affine thing. Thank you. All right, so construction. So let's let X be a regularly stratified scheme, and let's fix C inside X a stratum. Okay, so I'll denote by n plus xc. Simply, this is the normal cone. The normal cone of the closure of C in X. Okay, so remember this is i.e. this is simply the spectrum of direct sum of you take the ideal defining C bar power n, ideal defining C bar power n plus 1. So just a normal cone. Now, so it turns out that so the point is that here is that this has a natural regular stratification induced by Cx, and we can define it as follow. So we consider a so-called deformation to the normal cone. Let me remind you, this is a diagram like this, E1 times X, immersion, open immersion to some space called the deformation space, and then you have a close immersion from the normal cone. This is over O, this is over A1, this is a zero section, and this is E1. Okay, and so remind you, what is this deformation? So this is an open subset of the blow-up of C bar times O in X times A1. and you remove the proper transform of x times 0. So this is what is the deformation? This is normal cone. Right. So now let's how do we use this to get this stratification on n plus c? So so since x is regularly stratified, there exists there exists unique d inside x, a normal crossing divisor, which defining the stratification. So what you do, you simply you look at take the proper transform of d times a1 in the deformation space, and take the fiber at 0. So this gives you a normal crossing divisor in n plus xc, and this defines a stratification on it. Okay, and the open stratum. So this will be there will be a unique open stratum. So the unique open stratum is denoted by n circ xc. So this is a construction. Okay, so I can say some facts about this. So here's maybe complement or facts. So let's call Vxc the smallest constructible open neighborhood of C in X. So let's denote by Rxc. This is the lattice of constructible Cartier divisors on Vxc. So this is a finitely generated, something like z up to zn, number of reducible component. And then so So this has an order. This is an ordered group. The positive element are the effective divisors. And then so we given V in Rx, right? So a divisor that I write V, we define. We can put I bar V to be the quotient of the ideal defining V, modulo the ideal. So this is a fractional ideal, modulo V prime bigger than V of IV prime. Okay, so this is some kind of an this will be an OC module, and in fact this N0 XC is simply the spectrum of this graded algebra. And so in particular, you see that this has a structure of a torsor over some torus. So this tells you that N0 XC is a torsor over something that I call TXC, which is by definition the torus having RXC as a group of co-characters. So that's a torsor over cis on defined on C. Okay. And so in fact the compactification is also this nx plus c, this partial compactification is equivariant. This tx c equivariant. And so the action extends to n plus xc. So I need to list now some functoriality properties of this construction. I do this without proofs, and the proofs are really very easy. So let's take morphism of regularly stratified schemes that taking open strata to open strata. Okay, so let D be an SY stratum. So a stratum in Y. And and C F lower star T. So the stratum that contains the image of T. Okay, so there is an induced, as you might expect, morphism from n plus yd to n plus xc, just stratified. So again, it's a stratified morphism, which is also TYD equivariant. And it also takes the open stratum to the open stratum. So taking n0y d2 and 0xc. Here's another proposition. So here we take again x regularly stratified. And now we take an immersion y into x. So we'll be an inclusion. So let's say a regular constructible locally closed immersion. So by this I mean that, in particular, the stratification of y is the one induced from the stratification of x. Okay, so let C be an Sx stratum in y, so contained in y. Okay, then there exists there exists a natural morphism of lattices denoted by S flat going from R y c to R x c. Okay, I will not say what it does. Maybe I say it later. And a morphism of stratified schemes that goes in the opposite direction, nx plus c to n plus yc, which is equivariant for the action of txc. And so, of course, TXC acts here via somehow the dual of this map. Okay, so I just maybe say it orally. What is this thing here? I mean, this is just a free Z module on the reducible component of the divisors that define the stratification around C, right? And to each such thing, there is a unique reducible divisor which contains it. And you map it there. This is a map of. Okay. Think about it for a minute, and you see it's clear. So here's also something maybe I just write it down. So if you have such diagram, so these are like in this is like in the first position. This is like in the second one. Namely this takes open stratum to open stratum. This is a locally closed immersion. And so then you have the an induced. So you take a stratum here. You get this. Sorry, take a stratum here. Its image. So this is the image here, and you get this square, and this square is commutative. Okay, that's okay. So here's another lemma. Maybe the last one about these kind of functorialities. So here we take X regularly stratified. We take D inside X stratum, and we set Y. So we define Y to be n plus X XD. Then we take E a stratum in Y. Now this Y has a map to X and even more to the closure of D, right? So closure of D is the base of this torsor. So we can take C inside X, and in fact it's inside D bar, the image of E. In fact, here the image of E is really a stratum, so there is no need to say a stratum that contains the image. Okay, so in this situation, then there is a canonical isomorphism between the normal cone of X at C and n plus X and the n plus O. This is X. Like this. Okay, so I also won't say anything about the proof. Okay. I mean, if you try to imagine this is quite clear. It's not so surprising. All right, so now we come to an important construction. So this is the construction. In fact, maybe not a construction, but rather a notion. So this is the notion of tangential morphism. Tangential So we take x and y be two regularly stratified schemes connected. So I only consider tangential morphism between connected guys like this. So a tangential morphism that I write so as a couple fc from y to x. So is a pair consisting of two things, so of an Sx stratum C and a morphism of stratified schemes between y, so this is f, between y and the normal cone n plus xc, taking the open stratum to the open stratum n0 xc. So this is what is a tangential morphism. So up to now, it's no construction. It's just a definition. So the construction is of the composition. So given a second such thing, so GD going from Z to Y, the composition is defined as follow. Okay, so how do we define the composition? So let's see. Okay, so yeah, so we have this map from y to n plus xc, and so we let E be the stratum of n plus xc that contains the image of T. And furthermore, let F inside X be the stratum, which is the image of E. Yes, then we define this composition FC composed with GD to be H F, where H is the following composition. So as you imagine, so you can go from Z to N plus GY. This is G. Now, since Y takes the open stratum to the open stratum, by the first proposition, we have an induced morphism from the normal cone to the normal cone of N plus XC at the stratum E. And then by the last lemma, this is the same as N plus XF. And so this is H. Okay. All right. So connected regularly stratified schemes plus tangential morphism. So this is a category, and it will be denoted by regular tangential stratified over a basis or over a field. Usually, I think it will be always over a field. Okay. And there is a foliated version. Where and it will be denoted by reg fol d sigma k. Okay. Maybe let me put it here, so maybe a small remark might come up later. There exists a functor from regularly stratified tangential morphism to just reg sigma k. What does it do? So it's identity on object. And if you have FC, this goes to the following composition. You take the map F, and then you project to X. Okay, and this is a well-defined functor. You check it very easily. Oh, I mean, normal cones, tangent, vectors. Yeah, I don't know. Yeah, I mean, it's a map which remembers. I don't know. It will become clear when I will use it. So this has to do with this construction of, for example, of limiting Hodge structure and things like that, and where somehow, yeah, I mean, usually these constructions somehow they depend on the choice of a tangent vectors, but if you don't choose a tangent vector, then somehow you go to the normal cone. I don't know. It's just a name. I don't know. I don't have really a good reason. So it could be called a normal morphism, maybe. I don't know, but I call it tangential morphism. Okay, so here's another notation. Again, same X regularly stratified scheme. Now we take, instead of taking a stratum, I take a flag. In X. And so I define m plus X of a flag, right? So in a similar manner as before, but simply as follows. So I just take the n plus, but now not of X, but rather of the largest stratum closed of C0. This is the definition. With, of course, with the stratification, with its stratification. And inside this, we have the open stratum, which is M0XC. This notation. Okay, so why do we introduce this? Because of the following proposition. So there are two parts. So again, X regularly stratified. Then the map from taking a flag to this M plus XC extends naturally into a functor from the category of flags. So functor M plus X from flags on X to this category of tangential morphism, like T sigma K. Oh, I'm going very quickly today. So then part B is just somehow continuation, if you want, of A. So say that the previous functor, in fact, extends or give a functor like this from so a functor that I denote by M plus. That goes from this category integral over regularly stratified scheme of flags, of their flags, to this category of tangential morphism. Like which okay, of course, take X. So here, the objects are given by pairs of a regularly stratified scheme and together with a flag. So it takes such a pair and send it to m plus xc. All right, so this is the proposition. Again, I will not prove it really. I will just, I mean, it's of course not hard at all, but a bit tedious to check that everything is working. So I will only somehow discuss part A and try just to convince you that there is indeed such a functor. Okay, so let's fix a morphism in flags of x. All right, let's write C0, Cm, and D is D0, Dn. And so we will distinguish cases, in fact. And then, of course, the whole thing is to check that this is coherent and defines really a functor. Okay, so let's see. First, let's assume that that C0 is equal to D0. Okay, then in this case, it's easy. So of course, then the closure of Cm is inside the closure of Dn, and this is a regular closed immersion, which is constructible, and the stratification here is the one induced from here. So by one of the previous proposition, we have that there exists a natural morphism from n plus dn bar of d0 going to n plus of cm c0. If you remember that one of the propositions give me exactly such a map, and this is I mean, this is good because this is n plus by definition n plus d, and this is n plus xc. However, we will see in a moment that this is not exactly the right thing to take. I mean, first, of course, you don't need just a map. You need a tangential map. So, a tangential map is also given by specifying a stratum stratum here. And so I should tell you what is the stratum that you have to take. And so, in fact, the map that we take is the following. So, in fact, one should take rather the following thing. So I write it like this. So something which I will not specify, and then you have to take the stratum C0 and consider this as a map from, again, n plus, so maybe I write it like this, n plus d bar n d0 to n plus c bar. Okay, so what I'm trying to say here is the following. So I need to specify a tangential map between these two stratified schemes. So I need first to tell you which stratum you have to take. And so I say that you take the stratum C0, which is embedded here via the zero section, right? Now, if you take this stratum, then the normal cone is the same, does not change, and then you take the map that I just defined. Of course, there are different choices. You could also take the open stratum here instead of C0. But the thing that works is really is C0, which is I come to this also at the end of the sketch. So this is the first case. Now let's do the second case. So yeah, second case. Now let's take the opposite, so namely that assume that Cm is equal to dn. So in this case, we can write the normal cone at dn, so at d0, as follow. So first, so it will be as the normal cone of the normal cone of Cm at C0, and then at D0. And again, here D0 is considered, or D0 is embedded via 0 section. So we have this, and this defines to us a tangential morphism, namely identity, or this canonical isomorphism, and the stratum D0. This would be a map going from n plus dn bar D0 to n plus what is it? Cm bar C0. So these are the two cases. And of course, if you compose these two cases, you get maybe more interesting or really true tangential morphism. Things are given via so. I mean, in fact, maybe not here. I mean, in fact, maybe more interesting example would come in part B of the proposition, where you have a morphism of stratified scheme, and then this induces some maybe more interesting or tangential morphism. Okay. All right. So I wanted to. So this is my sketch. I want to make a remark. In fact, that in fact there is a problem in this proof, or even in this statement. The statement is not really true, because if you take the case, so yeah, if you take the case D equals C, right? So this would be the identity in the category of flags. This construction would give you the canonical map, but with C0 going from n plus right. And this is not the identity. It's different from identity, because I did not tell you what was the identity in the category of tangential morphism. This is the map given by taking the open stratum and the identity. So this is not the identity in the category of tangential morphism. But somehow there is no way to take something different here. If you want the two cases I discussed to be compatible while you intersect them, you have to take this morphism. So there's a trouble here somehow, and in fact, so the only way I know how to fix this is somehow to change. So one has to fix this. To fix this, one has to change the category of flags. So this is something that I denote in the paper. I think flag sharp. Which is basically obtained by adding an extra identity element to every object. So whenever you have a category, you can modify it by just adding formally adding extra identities everywhere, and then the old identity becomes idempotent, but they are not identity anymore. Or no, yeah, idempotence. Yeah, there is a construction like this that you can make. I mean, it's not and then one has to check that this does not modify somehow the Godman resolution up to homotopy and so on, but it's true. Yeah. Maybe there are different ways to fix this, but this is the one I found. And somehow I will ignore somehow this issue later. I mean, I don't want to discuss this, And so I will do as if this is well defined, that this is really a true functor. It's not so important, I think. Okay, so yeah. I mean, I could go on maybe for half an hour, or we can take a break and then continue. I don't know. Any preference? So I finish maybe, and then do you have a preference? Andrew? Okay, let's finish. Yeah? All right, so this is the next paragraph. It's about, so it's again about regular stratification. This is part 2, and it will be about modules with integrable connection. And let me maybe first motivate a little bit what we want to do now. So remember, we have these Godman complexes. And we want somehow, we want to make them a bit more algebraic. So we want to get rid of completions. Get completions. And the way this will be done is as follows. So this will be done. So this is done by replacing the completion. And remember, what the completion were given. Again, these were completion along flags. So whenever I had, so if you want, replacing the functor that takes a flag D and some stratified foliation X and send you this completion. Right. So remember, if you remember, the definition of this Godman complex was somehow using exactly these kind of completions. So we want to replace this by the similar functor that I introduced, by the functor which takes D again in flag X. Now, so here, I mean, of course, you assume that Sx is affine to make sense of this. Here we need to assume more, or somehow there's maybe a different condition, but somehow it's a construction of kind of a similar nature. So to a flag D, we take this m plus xt. Here, of course, Sx is regular. Okay, so the idea is that we want to replace these completion by this stratified thing. And in fact, to be precise, I don't want to replace them by this, but really by their open stratum. And somehow the idea, so in order to be able to do this, so in order to be able to do this, we need a way to compare. So we need to compare the RAM cohomology, or to compare the theory of the RAM local system on star. Star is this one. Is this diagram maybe? And let's call this double star. On star with the same thing, with the same on star star. Okay, so and this is somehow the goal of this paragraph is to make this possible. And so today I finished with this, and next time I'll tell you how this can be implemented somehow to get a better model of this complex. Sorry?
You're always somehow replacing the left-hand side with FL sharp. What you just said is.
Yeah, you mean I should be writing FL?
No, don't write it. But in fact, you're doing it.
Yes. I will do it. I mean, yeah. I mean, here there's no need for this, but there is need for this. I mean, when you deal with completion, there is no.
Sure, but when you compare them.
If you want to compare them, you have to. Yeah. Okay, so maybe some notation that I will be using now. So if X stratified, not necessarily regularly stratified, as usual. I mean, I said I've used this before, but let me make it precisely. So X0 will be the union of open strata, and partial X will be X minus X0. In the case of a regularly stratified scheme, this will be the normal crossing divider that defines the stratification. So here's a definition. So now let's take X to be a regularly stratified foliation. So denote by by make big 0 rs x. This is the category of I think it's called this modules with integrable connection on the open on x0 with regular singularities with regular singularities along the boundary. Okay, so if an object here, so it will be a module over x0, and as an OX0 module, it will be locally free of finite rank. And there is a condition that on the boundary, the singularities are nice, are called regular singular. So maybe I say a couple of words about what this means, since I have time. Okay. Make a necessary remark. So the notion of regular singularity is a classical one, I think. And there is this book of Deligny where he studies this, one book. So, but somehow, so classically, regular singularities are considered on, let's say, smooth varieties, smooth schemes over finite type over a field, and it's an absolute notion, and it is an absolute. I mean, at least in the book of Deligny, I think it's an absolute notion in the sense that what you do, you have your smooth variety, and then you take a compactification. And then you define the notion of regular singularities with respect to this compactification, but then you show that it does not depend on the choice of the compactification. So somehow it's an absolute notion. It's not relative to a fixed divisor. I mean, classically, of course. But there are many authors who developed maybe a more general situation. So, for instance, so that there are many authors who also looked at more general basis. I don't know, let me put some names. I don't know, probably Malgrange. I don't know. There is also Kedlaya. And probably there is this book of André Baldassari. Okay, so there are many ways to define what it means to be regular singular. So I will give you one way, which is somehow if you want the concrete or naive way, and this is enough for what I want to do, and I think it's maybe the easiest way to do. So I'll give you concretely what I mean by this. Try to make this definition precise. Yeah, so somehow the definition I will give you is maybe not very satisfactory because somehow it's, we'll see it somehow it's given by generating some subcategory of module with integral connection. But somehow there are, it will be enough for what I want to do, and there are theorems which tells you that in the case of algebraic varieties, it gives you the right definition. So somehow it will be enough to work with. Okay, so let me explain this. Okay, so here's maybe definition continued. So, okay, so we say that, so let's take M on x0, assumed to be this. So, as I said, this means that it is, as an OX0 module is locally free of finite rank. So we say that M has regular singularities along the boundary if the following hold. So for every stratum inside X, the pullback of M to the completion at C and take 0 here. So of course the completion has also a stratification, and you take, so this is the inverse image of x0 in the completion. So we want this M to belong such that M belongs to the smallest subcategory of module with integrable connection on x hat C0. Stable by say by extension and tensor product, and containing the following example. I mean the following objects. So of course we want this to contain the image containing, so the image of make of the whole, so of x0. Of course I want this to be smooth, so this, let's say, the base change. Okay, I want this to be here. And so, for instance, you see that you have all the things of logarithmic type, for instance, because these are extension of trivial modules. Okay, so they are there. And then there are these guys. So here's, I give you what it is. So let's call it like this: RAT. So this is as a module, it's given by OA, so it's free of rank 1, and it's generated by essentially t to the power a, where a is a constant, and t is a local, so it's generator of the ideal of some divisor, where d constructible divisor. Constructible smooth divisor. Okay, so it's like, I mean, this is like, you think about this as a function, so it's like the function to some power, 1/3, but any constant also work. And so the point is that the derivative of dt of dA, this is of course a dt t a over t dt. Okay, so you have this. This is the rule of the derivation here. Okay. All right. So these, the things that are generated by these guys are are known to be the only example of thing of which are regular singularities. Yeah, and so I take this as a definition, if you want. And it's known that over an algebraic variety, this is the right definition, or it coincides with the right one. Okay. Okay. All right, so why do we restrict ourselves to these regular singular modules with integral connection? Is because of the following theorem, which is not true otherwise. So let again x be regularly stratified foliation. C inside X is stratum. Then there exists a canonical monoidal functor that so noted by psi C, which goes from a modular integral connection, regular singular on X, to module with integrable connection, regular singular on n plus xc. So this is what I was referring to some minutes ago, so-called the limiting construction of so in this case of modules integrable connection. And so moreover, if X is affine and complete, along its closed stratum, which may not be C, but then this functor is an equivalence of category. Okay, so the second part is not really so difficult or surprising. It comes from the fact that we know, I mean, of this description, we know exactly how we generate the category of module integral connection in case X is complete at the stratum. Okay, so it's just the construction of this thing is due to the linear. So comment maybe. So the construction of psi C is due to the linear again, in this short and nice book about regular singularities, and somehow the idea. So very quickly. So what is the idea is to use the so-called the so-called the linear extension. So every such every module which has regular singularities extends to X, not as a module with connection, but as a module with logarithmic connection. So the connection would go to not to n tensor omega, but to n tensor omega log d, where d is a divisor at infinity. So in fact, this is also one characterization of regular singularities, is such that such an extension exists. And when you have such an extension, then then this is a construction which is essentially given by taking the graded of something. And I mean, you see, this is somehow the spectrum of the graded of some filtration on OX, and you extend this construction, and you get your modulus essentially. Okay, and then you show that it's independent of the extension. So the linear extension is not always. I mean, it's not unique, but then what you get is independent of this. Okay. Okay, so what we get from this is the following corollary. And this is really exactly the reason why when one has to deal with this tangential morphism. So there is a canonical two-functor that goes which is denoted by mic, or which is denoted by mic or S0, and it goes from the category of regular foliation, stratified, and with tangential morphism over K to cat of categories, and sends X to make 0 regular singular X. Okay, and so what does this two-functor do? So it takes a tangential morphism Fc from Y to X to the following composition. The composition So you want to go from make 0 regular singular on x to y. So you first apply this limiting functor, the Lean's limiting functor, psi c, to go to make 0 regular singular, and now you are over the normal bundle of x c. Good. And now you can really apply f upper star to go to make 0 regular singular y. And the reason why you can apply f upper star is exactly because, remember, in the definition of a tangential morphism, we asked that f takes the open stratum to the open stratum. Okay, this is, of course, essential. Otherwise, you don't have this f upper star. All right, so this is the corollary. Okay, so now I can give you now the tool how to compare somehow the de Rham story over the completion and the de Rham story over these normal cones. Or okay. So now let me write down the construction and then state the theorem, and then will be the end of today's lecture. All right. Okay, so let's recall what we have. So recall that we have a functor like this, going, so it's called m plus, and it goes from this category integral over regular foliation stratified over k flags, going to regular foliation, but with tangential morphism. Okay, and then this is sending x to m plus xd, and so sending x flag to m plus xd. Okay, now we can by the previous corollary, I can go further, and I can compose this with this guy. Let's call this m plus. And this is amic. Okay, so we get in this way the functor make 0 regular singular composed with m plus. Okay, so yeah, it takes xd and send it to make 0 regular singular on m plus xc. XT. Okay, so this is one functor, or two functor, pseudo functor. Let's call this star. And on the other hand, we have another one. So on the other hand, we have also going from the same category, regular foliation, stratified. Yeah, okay, over K. Yeah, okay. I mean, here I don't need, okay, let's do it in general. So take, here we can go from excellent foliation, but I have to put affine. So of course there is a big intersection between these two categories. Flag, again to cat. And now it takes a pair like this and send it to a module with integrable connection. Just put let's put smooth or less. Over x hat d. And let's call this mic over hat. Okay, so this is my second functor. All right. So we have these two situations. This was responsible of. I mean, this was essentially used in defining this formal Godman resolution, or if you want, we can reformulate the complex that we had at the last theorem today using only this two functor. And so what we want to do, we want somehow to replace the use of this two functor by this one, and so the next theorem somehow give us a way to do this. So I'll state it now. So here's the theorem. It's very simple. So saying that if you restricting to this subcategory consisting of regular foliation, which are affine stratified of flag. So the second we have a pseudo-natural transformation from the first one to the second one. So from mic 0 regular singular composed with m plus to mic of course, it's not enough just to, I mean, we need some information, but I will not write anything about this. I will just give you the construction of this pseudo-functor at a fixed pair xd, and I mean later when I use this, I maybe in some special cases I prove something about this functor. But so let me just give you the construction of this. So here's proof for construction. So fix X regularly stratified foliation and the flag C. So, all right. So the function is given by the following composition. So we take the following composition. Okay, so we want to go from mic 0 regular singular over this m plus x c. Okay, so this is by definition, or not really by definition. No, it goes to the following thing, to mic 0 regular singular simply of the normal cone at Cm C0. So what do I mean by this? So this has inside it n0. As an open set, and so it's regular singular with respect to the boundary of this, which is somehow smaller than the boundary here. So this is why you have just an inclusion, in fact. Okay, so this compactification is smaller than the one that is natural here, because I did not take, if I would take C bar, then this would be the same. I took the normal cone of C0. Okay, so this is a smaller compactification, and therefore the condition of being regular singular is a weaker one than here. So we have this inclusion. Okay, but then this is the same as the category mic 0 regular singular of the following thing. So you take Cm, you complete, sorry, Cm closer, and then you complete with respect to C0. Okay, and why these two things are the same? This is, I mean, actually the functor goes like this, and this is C0. And we know that these are equivalent because this guy is complete at C0. It's a regular foliation which is complete at the closed stratum C0, and this is why somehow I had to force C0 to be a closed stratum. Okay. Okay. Is it okay, Andrew? You can ask a question. No? Okay. So now this guy is, yeah, now this goes to, yeah, I mean, again, you have inclusion to, now we just take all the list one. But now it's, what do I want to say? Yeah, it's, okay, so this is C hat, M, again completed at C0, but now you take the 0, the open stratum. Okay, so I just, here I had regular singular along the boundary, and now I just forget the boundary, I map it to this C0. Now this guy receives the category of mic list of x, of the completion of x along the flags C0 Cm. This is just so this is a closed subset. This is a closed stratum, if you want, here. This guy here. This is a closed stratum here. Right? So here I complete first for C0. I take the inverse image of Cm and I complete again. And I see this guy as a closed subset there. This is where I mean, this is a closed subset where this guy is complete there. But since this is complete along this is also an equivalence of categories. Okay, and now we are done. We can map this guy to make this of xc. Okay, so this is the construction, and you see, I mean, several of these maps are equivalences. So if you want to understand what's happening, you can, yeah, it's enough to understand. I think this map here maybe. I mean, this is somehow the most important map. Maybe I don't know. Yeah, no. I mean, okay, there's not. Sorry. Right. So I think I stop here today, and so next time I will use this, and maybe with some more information about these functors here, somehow to get rid of completion. Okay. Any questions?